You are Arthur Eddington, and a torrential downpour is about to ruin the most important 6 minutes of your life. The date is May 29, 1919. You are on the island of Príncipe, a tiny volcanic rock off the coast of West Africa. The air is thick with humidity, and a thick blanket of gray cloud conceals the sky. In minutes, a total solar eclipse will begin, and you have gambled your career and the reputation of a German physicist named Albert Einstein on getting a clear photograph. The sky darkens. The rain stops, but the clouds remain. It is a complete failure. Then, through a sudden miraculous thinning in the clouds, you see it, a black disk surrounded by a ghostly silver halo. And next to it, faint points of light. The stars have come out in the middle of the day. Here is how you arrived at this moment. The year is 1917. You are at the Cambridge Observatory in England. The Great War rages across the Channel, a conflict that has severed scientific communication and pitted nations against each other. You are a Quaker, a conscientious objector, and your refusal to fight has put you at risk of imprisonment. Your salvation arrives not in a military deferment, but in a scientific paper. It comes from the neutral Netherlands, written by the physicist Willem de Sitter. It describes a radical new theory of gravity, conceived by Albert Einstein in Berlin. You are one of the few astronomers in the world with the mathematical skill to truly grasp it. The theory is called General Relativity. It proposes something that sounds like fantasy. Gravity is not a force pulling objects together. It is a curvature in the very fabric of reality, a fabric of space-time. A massive object like the sun doesn't pull the Earth. It creates a deep well in space-time, and the Earth is simply rolling along the edge of that well. It is an elegant, revolutionary idea. But without proof, it is just an idea. Einstein's theory, however, makes a specific test-stable prediction. If the sun truly warps spacetime around it, then the light from a distant star passing near the sun should follow that curve. From our perspective on Earth, the star's position in the sky will appear to be slightly shifted. Isaac Newton's laws also predicted a slight bending of light, but Einstein's theory predicted a shift twice as large. The Newtonian value is 0.87 arcseconds. The Einsteinian value is 1.75 arcseconds. An arcsecond is a tiny unit of angular measurement. It is 1/3.6 of a degree. Measuring it is like trying to spot the width of a human hair from over 20 meters away. You cannot see stars when they are next to the sun. Its glare is too powerful. But there is one exception. During a total solar eclipse, you consult your star charts. The astronomer royal, Frank Watson Dyson, has already identified the perfect opportunity. On May 29, 1919, a total eclipse will occur, and a cosmic coincidence will place the darkened sun directly in front of a rich star field known as the Hyades cluster. Its bright stars will provide the perfect reference points. The stakes are immense. If you measure no shift, Einstein is wrong. If you measure a shift of 0.87 arcseconds, Newton is still correct. But if you measure a shift of 1.755 arcseconds, you will have proven that the fundamental nature of the universe is not what humanity has believed for over 2 centuries. Dyson uses the importance of this mission to save you from prison. He argues before the government that your scientific expertise is vital to national interest. The expedition becomes your alternative service. A British scientist, spared from the war, sets out to test the theory of a German scientist. In a world torn apart by nationalism, this is an act of scientific faith. Planning begins in earnest. An eclipse is a fleeting event, and weather is the ultimate variable. You cannot risk a single cloudy sky. Dyson's strategy is to hedge the bet. 2 expeditions will be sent to 2 different locations along the path of totality. You will lead one team to the island of Príncipe. The other team, led by astronomers Andrew Crommelin and Charles Davidson from the Greenwich Observatory, will travel to the town of Sobral in northern Brazil. At least one of you, you hope, will have clear skies. The equipment is prepared. There are no digital cameras. You will be using large, heavy photographic plates made of glass, each one sensitive to light. The core of your instrument is a 13-inch astrographic lens, loaned from the Oxford Observatory. To keep the sun centered in the frame, you have a colostat, a clockwork-driven mirror that will track the sun's motion and reflect its image into the fixed telescope. In March of 1919, you board the steamship Anselmset. The journey takes weeks. You and your colleague, a clockmaker from Coventry named Edwin Cottingham, watch over the precious crates of equipment. You arrive on Príncipe in late April. The island is a former slave port, now covered in cocoa plantations. It is beautiful, but the climate is your enemy. This is the beginning of the rainy season. The air is heavy and damp, a constant threat to your delicate photographic plates. You set up your instruments on a plantation, building a makeshift observatory. Each night, you take practice exposures of the sky, calibrating your focus, rehearsing your movements. The entire observation during the eclipse will last just over 5 minutes. There is no room for error. You must be a machine, executing a precise sequence of actions in near darkness. You must swap out 16 heavy glass plates, making sure not to jostle the telescope, all while the clock is ticking. In Sobral, Brazil, Cromlin and Davidson face their own challenges. The climate is hot and dry. They set up 2 telescopes. Their primary instrument is a 13-inch astrograph, similar to yours. Their backup is a smaller, 4-inch telescope, which they fear may not have the resolution to capture the tiny shift. The days tick down. You watch the sky over Príncipe with growing anxiety. It is often cloudy. Local residents tell you the morning of May 29th is almost always clear. You hold on to that hope. The night before the eclipse, you can barely sleep. You have rehearsed every step. The plates are loaded. The telescope is focused. The coelostat is wound and running. Everything that is within your control has been controlled. The rest is up to the sky. You wake before dawn on May 29th. Your heart sinks. A thunderstorm is raging. Heavy rain hammers on the roof of your hut. The sky is a wall of gray. This is not just cloudy, it is a washout. As the morning progresses, the storm subsides, but the clouds do not break. The predicted time for the start of the eclipse arrives. The light begins to fade, an eerie, unnatural twilight. But it is a twilight seen through a thick screen of cloud. This is a disaster. 2 years of planning, thousands of miles traveled, a world waiting for an answer, all for nothing. You look at Cottingham and speak the honest truth. You do not think you will be able to do anything. Totality begins. The world goes dark. You are in the moon's shadow. And then, you see the first hint of a miracle. A patch of sky directly around the sun begins to thin. The clouds are not parting, but they are becoming translucent. You can see it. A ghostly halo of light. The sun's corona, visible only during an eclipse. And through the haze, like faint diamonds on gray velvet, you can just make out a few of the brighter stars of the Hyades. There is no time to think. You begin the sequence. Exposure 1 now. You call out. Cottingham works the shutter. You count the seconds aloud. You move with frantic precision, removing the massive plate holder, inserting the next one, your hands steady despite the surge of adrenaline. The clouds are a constant torment. A star might be visible for one exposure, then gone for the next. You can only see 2 or 3 stars clearly. You need more for a reliable measurement. Halfway through the eclipse, the clouds thin a little more. For a precious minute, the view is clearer. You expose several plates in this brief window. Then as totality ends, the clouds thicken again, swallowing the sky. It is over. You have taken 16 photographs. But looking at them, you can only be certain that a few will have any usable data. You do not know if it is enough. Thousands of miles away in Sobral, the sky is brilliantly clear. Cromlin and Davidson perform their own sequence flawlessly. But they face a different kind of crisis. As they develop their first plates, they see that the stars on the images from their main telescope are out of focus, slightly blurred. They realize the sun's intense heat has caused the coelostata's 16-inch mirror to expand and warp, ruining the delicate focus. Their primary instrument has failed. Their only hope rests on the plates from the small 4-inch backup telescope. They had considered it an afterthought. Now, it holds the key. The journey home is long. You cannot perform the final, delicate measurements on the island. You develop a few plates to confirm you captured images of stars, but the true work must wait for the precise measuring instruments back at Cambridge. For months, the scientific world waits. You return to England and begin the painstaking process of analysis. In a darkened room, you place a plate from the eclipse next to a comparison plate of the same star field, taken from Príncipe months before the eclipse when the sun was not there. You sit at a micrometer, an instrument that allows you to measure tiny distances on the glass. You are looking for a shift of less than a 50th of a millimeter. It is tedious, eye-straining work. The cloudy background on your Príncipe plates makes measurement incredibly difficult. After weeks of work, you derive a value. It is 1.61 arcseconds. It is noisy. The margin of error is large, but it is much closer to Einstein than to Newton. Then the plates from Sobral arrive. The news is mixed. The blurry images from the main, warp telescope give a result of 0.93 arcseconds, a number that seems to support Newton. But the plates from the small 4-inch backup telescope are perfectly sharp. The stars are clear points of light. When Crommelin measures these plates, the result is unambiguous. They show a deflection of 1.98 arcseconds. Allowing for the margin of error, this is a direct hit for Einstein's prediction. You, Dyson and Crommelin now face a critical scientific decision. You have 3 sets of data. Your cloudy results from Príncipe that lean towards Einstein, the blurry Sobral results that lean towards Newton, and the clear Sobral results that strongly support Einstein. You make the judgment call. The main telescope at Sobral was compromised. Its mirror demonstrably warped, producing poor quality images. That data is unreliable and must be discarded. The scientifically sound data comes from your plates at Príncipe and the backup telescope at Sobral. Both, despite their individual challenges, point to the same conclusion. On November 6, 1919, you stand before a packed joint meeting of the Royal Society and the Royal Astronomical Society in London. The portrait of Isaac Newton hangs overhead, a silent observer. The tension in the room is palpable. The Astronomer Royal, Frank Watson Dyson, takes the podium. He calmly lays out the evidence. He explains the 3 possibilities: no deflection, the half deflection predicted by Newton's laws, or the full deflection predicted by Einstein's theory. Then he delivers the verdict. After a careful study of the plates, he announces, "I am prepared to say that there can be no doubt that they confirm Einstein's prediction." The results of the expeditions to Sobral and Príncipe leave little doubt. A wave of shock and excitement ripples through the hall. The president of the Royal Society, J.J. Thomson, the man who discovered the electron, rises to speak. He declares the result is not the discovery of an outlying island, but of a whole continent of new scientific ideas. He calls it one of the greatest achievements in the history of human thought. The next day, the headlines blaze across the world. Revolution in science. New theory of the universe. Lights all askew.